recording. All right, rules. For anti-differentiation. And there are some rules that you are more intuitive than others, and others you'll have to just memorize so that you can keep those all straight. All right, what I just want to officially get down on paper is the rule that we just went over with Abby and with Joanne. Okay, so this is called our power rule for antiderivatives. We have a power rule for derivatives. We have the power rule for antiderivatives. So if the derivative is x to the n, as long as n is not equal to -1, that is the one exception for when n is equal to -1. It doesn't work. As long as that is true, then the derivative is defined as the increase of the power by 1 divided by the value of the new power, and then plus a constant. So that is your power rule. And then following up on that, we need a rule for what do we do when n is equal to -1? What do we do when in that one instance? All right, so Bella, why is it a problem for n to be equal to -1? Okay, because the result then would give me dividing by 0 if n was equal to 1. So then we need the rule for a logarithm. So we have then our logarithm rule. And so then we've got, if f prime of x equals x to the n when n is equal to -1, then the antiderivative for that, that's the one situation where you'll have the logarithm of the absolute value of x plus c. So it is tempting, especially when you see negative powers, to just assume that a logarithm goes with that automatically. But it doesn't unless that power is just a single power of n to the -1. Okay, then we have our inverse trig rules. Because that builds onto it a whole other set of fractions. 1 over. It is tempting. Okay, let me pause this. Come back here. So if you have f prime of x being equal to plus or minus 1 over the x squared plus 1. Okay, either one, either positive or negative. Then that is going to be solved by f of x being equal to, this is a situation of inverse trig. Do you remember all your inverse trig rules? 1 over x squared plus 1 came from the derivative of the inverse of tangent or the inverse of cotangent, depending on if it was positive or negative. Those two go together. It's like, oh man, I haven't done that since October, and I have to remember what those are. Okay? So that's just going to be something that your brain is going to have to pull back out of its memory. I knew that derivative at one point in time, so now I just have to recognize that derivative that I knew before and pull it back. Okay, help me out. What are some of the other inverse trig derivatives?
Plus minus 1.
Okay, plus or minus 1.
For absolute value of x.
Ooh, she's starting with that one. Okay, absolute value of x.
Oh my gosh, minus 1?
Not minus 1, no. This was the hardest one. Rad x squared minus 1. Okay. All right. Well, that's pretty unique. If you see that, if you see something with an absolute value out front and the square root, chances are the problem is probably designed to have you recall the antiderivative of that is going to be, all right, Joanne, what is it? Which ones do those match to?
Sine?
No, it's not sine. Okay, it's either secant inverse of x plus c or cosecant inverse of x plus c. All right, that's that one. Okay, so it's a pretty unique one. It stands out. 1 over the absolute value and a square root and a square. It's going to hopefully stand out to you. All of your problems tonight are designed. Okay, so this is just introductory. You know, they're all designed to match something that you've already seen. All right, so what's the last set of inverse trig rules? Okay, plus or minus 1 over. What was the last one?
Square root of 1 minus x squared.
Very good. Square root of 1 minus x squared. That was the other one. So it doesn't have the absolute value, and the subtraction is the reverse of that. So, Blake, then, what is the antiderivative?
Inverse sine.
Okay, so this is inverse sine of x plus c or inverse cosine of x plus c. And how did we remember which was which? All the cos are negative, right? All the anything cotangent, cosecant, cosine, inverse, all of those are associated with the negative value. Okay, good. All right, our last set of rules. So we've got so far power rule, logarithm rule, inverse trig rule. The other ones you'll need to recognize on site are just the regular trig rules. And these are for anti-differentiation. So again, these are going to be set up in recognizable form. Okay, set up in recognizable form. So if f prime is cosine, then what is f?
Sine.
Okay, sine. Those go together. If f prime is sine, very good, negative cosine. All right. How about if f prime is tan? Temeskin says secant squared. That's the derivative of tangent. I'm not being very nice here, I don't think. Okay? Is tangent anybody's derivative?
No.
Something.
Okay? Well, it's something, but it's not one of the 6 trig functions. Tangent itself is not the derivative of any of our trig functions. So right now, you won't be asked that. You will in the future. Okay? But right now, you're not going to be asked that. Whoops. Okay? I know. I'm sorry. Okay? So you're not yet. You will be. Okay? You will be later in the chapter, but you won't be asked that yet. All right. So then help me think of ones that actually are derivatives of something else. So, Temeskin, you were on the right track. Okay? Give me the one that you said.
So secant squared.
All right. You will be given secant squared. Because secant squared is the derivative of tangent. Very good. Okay, we've got a couple more to go.
Secant x.
Josh,
That's what I was going to say.
which one?
Secant x tangent x.
Okay, so you were going to say the one that is secant x times tangent of x. All right, what is that one?
It's secant.
It is just secant itself plus c without the tangent. Okay, we got 2 more.
Negative.
They're kind of similar to the ones we've done already. Abby? Okay. Negative cosecant squared. And so then that antiderivative would be, go ahead, Abby. Or do you want to do it the positive? Were you thinking positive? It's up to you.
Negative.
All right. If this is negative, then its antiderivative is positive cotangent x plus c. All right. If it was positive, then its antiderivative would be negative. right? Either one or the, excuse me, one or the other. Okay, it's one, either one is negative and the other is positive, so that's fine. Abby, for you to, either one. Okay, you should be able to go either one. And we've got one more. Okay, so negative cosecant x cotangent x. So its antiderivative would be positive cosecant of x. Or if you had the opposite, if you had the positive derivative, then the antiderivative would be the negative part. Okay. These particular sets of derivatives are derivatives and antiderivatives are set up for you in a particular way. They all have a perfect match. Your homework tonight, everything will have a designed perfect antiderivative. Okay, you will learn over the course of the next couple of weeks other skills, other methods to find ones that are a little bit more complicated. You know how, like, same thing with derivatives. We learned chain rule and product rule and all those other things. All right, so let's practice these, with what I mean by design antiderivatives. First example might look something like this. You might be given a derivative, dy dx, so that's written in Leibniz's notation now, not necessarily f prime, which is how Newton would have written it, but Leibniz would write dy dx, same thing, it's still his recipe for derivatives, and it would be something like this: 10 square root x cubed minus cosecant squared of x. That is a designed problem. Each piece should match with a perfect rule, which would match with a perfect antiderivative. The first thing that would jump out to me in my experience of looking at that is that part of it that's the square root. For me personally, I would get rid of that square root and change the square root of x cubed into something that had a rational power, a rational exponent. So what would that look like instead? X to the 3 over 2. All right, so for me personally, I would get rid of that, even as I'm copying it from my textbook or something, and I would write x to the 3 over 2. Because that's a rule I can deal with. It's in a format that I can follow the x plus 1, increase the power, divide by the new power rule. All right, so in Leibniz's form, if the derivative is written dy dx and the antiderivative is just written as y equals. So then let's follow the rule. So this will be 10. It's a coefficient, so 10 just is going to stay through there. 10x to the, all right, increase that power, so how high does it go? 5 over 2. And divide by the value of that new power. So you're dividing by 5 over 2. And we'll clean that up. We'll simplify and reduce. All right, what about the antiderivative of the negative cosecant squared of x? Plus cotangent of x, and then also plus c. So we want to simplify that and clean that up. Anytime you're going to divide by a fraction, it's the same as multiplying by the reciprocal. So you might want to think of that as going, well, that's multiplied by 2/5 instead of dividing by 5 over 2. And so overall, we will end up with y equals 4, okay, 10 times 2/5, times the square root of x to the 5th, plus the cotangent of x, plus c. All right, how do you check your work? Take the derivative again. All right, just to double check that you didn't make a, multiplication error or division error or some kind of simplification error. If you are given, all right, so then if the equation also gave you and if the equation gave you 0, 2 as your particular initial point or your initial condition, then you can continue and substitute 0 and 2 into your new equation and solve for c. So this would be 2 equals 4 times 0 to the 5th plus the cotangent of 0 plus c, which means c is 2. So my antiderivative is 4 times the square root of x to the 5th plus the cotangent of x plus c. Example for today. Oops. Okay, dy dt. What that means is that we are relating the variables of y and times. This is likely probably a physics problem because we're using time. We're given 3 over t plus 3 over t squared plus 3 over rad t. Each of those has a particular rule, each piece. And so if I were you, again, I'm just going to encourage you, think of these in terms of their rational equivalents. So 3t to the negative 1 plus 3t to the negative 2 plus 3t to the negative 1/2. So think of each of those not as a fraction, but rather as their negative rational counterparts. Once you've thought of them that way, then apply the appropriate rule. So what's the rule for the first one? That's the natural log. That's the time where the power would be equal to negative 1. And so I will have 3 as a coefficient times the natural log of the absolute value of t. The rule for the second one, plus, now I'm going to have just my regular power rule, where I'm going to increase the power and divide by the value of the new power. So this will be 3t increased to a negative 1 dividing by negative 1. Yeah?
Do we have to add c?
We will at the, not each time, no, because there will just be one c at the end that will cover all of them. Sometimes in some other textbooks you might see plus a constant here and plus a second constant here and then a third constant at the end, and then you're like, we're just going to combine them all and they will just be plus c. Yeah. Okay, that's good thinking. All right, plus, now we're going to have 3t. This time we want to increase the power again just by 1. So when I go from negative 1/2 and I increase that by 1, now I'm positive 1/2 and I'm dividing by positive 1/2. And then there's the addition of a third constant. So I have 3 different constants for each piece. And so rather than write 3 separately, we will get rid of that one and get rid of this one and get rid of this one and just have 1 plus c that will cover the whole problem. So now we clean this up. So we'll have 3 times the natural log of the absolute value of t minus 3 over the fraction t plus 3/2 times the square root of t plus c. Oh, no, wait. It's not 3 divided by 2. What is it? 6. Thank you. I forgot to multiply by the reciprocal.